EES, which is pronounced EASE, is an acronym for Engineering Equation Solver. EASE provides property information for many different types of substances, and these include things like real fluids, ideal gases, and air-water mixtures. The brine property functions in EASE refers to the properties of mixtures of water and another substance that results in a reduction of its freezing point. So brines are sometimes also called secondary refrigerants. The properties of primary interest for brines are the specific heat capacity and the freezing point. The thermal conductivity and the viscosity of brines are also of interest because they affect the heat transfer characteristics as well as the pressure drop and therefore the pumping costs. Brine property correlations have been published by the International Institute of Refrigeration, and these correlations have been implemented in EASE. You can see the reference here. All of the brine properties are functions of temperature and concentration of the solute, with just a couple of exceptions that we'll go over here in a second. The property functions applicable to brines and the units of the values that the function returns are summarized in this table here. These functions are also visible in the function information dialog window when the brine button is selected as shown here, so you can see the functions. Each of the brine property functions requires 3 parameters, again with a couple of exceptions. The first parameter is always the short name of the mixture or the brine in question. So for example, EA is the short name for an ethyl alcohol water mixture. CaCl2 is the short name for a calcium chloride water mixture. The name can be provided as a string constant or a string variable. And as with all the other property functions, quotes around the string constant are not required. The short version of the fluid mixture names for which data are currently provided are listed in this table here together with their complete names. Of course, as with any type of fluid, new fluids are constantly being added to EASE, and so this list will grow with time. In addition to the short name of the brine mixture, most of the brine functions also require the temperature and the mass concentration of the solute, which is expressed as a percentage. So these can be specified using the indicators T equals and C equals respectively, and they can be provided in any order. The temperature must be provided in the units that are specified in the unit system dialog or by using the $unit system directed. The freezing point and the normal boiling point return the freezing points and the boiling point at 1 atmosphere, and therefore those two functions do not require temperature. They require the mass concentration only. And then the enthalpy function here also requires pressure, so it's going to require temperature, concentration, and pressure because enthalpy of an incompressible substance depends on pressure. So if we want to know the freezing and normal boiling points of a 40% by mass ethylene glycol mixture and water, we can use the freezing point and normal boiling point functions as I've done here. And you can see the freezing point has been substantially depressed relative to pure water, and the normal boiling point slightly elevated. We can get other properties of interest like the specific heat capacity, the density, the viscosity, and the thermal conductivity here for, again, a 40% ethylene glycol mixture, but now at a specific temperature of 10 degrees Celsius. And finally, we can evaluate changes in internal energy and enthalpy between two different states. So here let's use state 1 as 10 degrees Celsius, 40% ethylene glycol in 1 atmosphere, and state 2 will be 60 degrees Celsius, 10% ethylene glycol in 20 atmospheres. And here I'll evaluate delta U with 2 calls to int energy and delta H with 2 calls to enthalpy. So again, notice that the pressure is required to evaluate the change in enthalpy, but not the change in internal energy. If we look at the answer, you can see that the difference between delta U and delta H is really pretty small because the change in the product of pressure and specific volume is very small for these incompressible substances. And it's important to understand that the enthalpy of mixing is included in these calculations, and therefore changing the concentration as I did between these two states is okay. The internal energy is referenced to that of pure water at 0 degrees Celsius. One last note is that prior to ease version 8.785, Brine properties were not provided as internal property data in this way, and they were instead provided by an external procedure called Brine Prop 2. The Brine property data used for the internal Brine property functions that we just talked about in ease is based on newer correlations than what was used in the Brine Prop 2 procedure, and it's therefore suggested that you use the internal Brine properties. However, the Brine Prop 2 external procedure is still provided with ease for backward compatibility. Information about the Brine Prop 2 external procedure is available in the Function Information dialog window by clicking on the Ease Library Routines button and then scrolling to the Brine Prop 2.lib folder. And again, it's suggested that you use the internal Brine property functions rather than this Brine Prop 2 procedure, provided, of course, that you have a version of ease that's later than 8.785. This is one of a series of tutorials that is meant to describe the operation of the ease software. To get more information about ease, obtain the software, or access more of these tutorials, please go to the website fchart.com. These tutorials are excerpted from the book Mastering Ease, which can also be obtained from the fchart website.